So good morning, good afternoon. Welcome to this new webinar organized by the Maternal Health Supplies Caucus of the Reproductive Health Supplies Coalition. Please remain muted to prevent background noises from your homes or your offices. This webinar is being recorded and a link to the audio and video will be sent out to all our members at the Maternal Health Supplies Caucus in a couple of days. The recording will be stored in our website and in our webinar library, so you will have access to it anytime. You're most welcome to write your questions in the chat box. And without further ado, let me introduce our panelists, Ms. Kitty Liao. Kitty is the CEO of her own company. And today she's going to introduce herself and introduce her company and the products that she is developing. So Kitty, the microphone is yours. Thank you.
Thank you so much, Milka, and thank you so much, everybody, for joining today. So before we started, maybe some of you heard our conversation that, so my look or the picture that you were shown could be a bit deceptive. So I'm 37 years old, in case you're wondering. So today I'd like to share with you the work I've been doing on the last mile cold chain development of a cooling system. And before I started working on that, I was actually working in a different environment with systems that were immersed in cryogenics liquid, so superfluid helium at minus 270 degrees C. And then, so today I want to kind of bring you back a little bit to how it all started. So, oh, I forgot I didn't share my screen. There we go. Are you able to see the screen?
Yes.
Yes.
Okay, great. Yeah. Thank you. So, it all went back to 2014, so 7 years ago. I went to a humanitarian hackathon. And so this event was organized by people working at CERN. So CERN, where the big particle accelerator is. Maybe you've heard of it. It's called the Large Hadron Collider, based in Geneva in Switzerland. And that also happened to be where I used to work at. So 7 years ago, I went to this humanitarian hackathon, and the people who organized this event, who were really passionate about social problems. And so what they did was they put the staff members from the WHO, the Red Cross, these kind of organizations, and they sat down and said, okay, what are the most urgent problems that needed solving? And so these people, they came up with a few very, very big issues. And so what they did was they put together people from different backgrounds, so in technology and science and engineering and business and art, various backgrounds, and put them into teams and to tackle these problems within a very short amount of time. And at the end of it, they present a prototype. So I saw this event and I thought, wow, that is really interesting. And to my surprise, that I was really shocked by one of the problems that they presented, which was the vaccine spoilage at the last mile. So at that time, the WHO predicted the vaccine spoilage across the globe at between 20 and 50%. And at the time, 18.4 million children just didn't get any basic vaccinations at all. So polio, measles, yellow fever, that kind of thing that we had when we were little kids. So for me, that was just shocking because that was just something that I never thought of. And then so many people died of these kind of preventable diseases every year. And that just for me very shocking, that we're so advanced in technology, and we're still unable to keep vaccines cold just between 2 and 8 degrees at the last mile. So another shocking element was, besides people dying and vaccine being wasted, there's $1 billion worth of wasted happening every year. And that's excluding the amount of effort put into developing life-saving drugs or vaccines. And at the end, all those effort were wasted. So let's have a look at what a typical last mile journey looks like. So over here, you could see there's a bunch of pictures where these health workers, they'll carry these polystyrene boxes or plastic box that's filled with polystyrene. So basically, it's a cool box. So it's got a box and a lid, and that's it. And all of them require 4 ice packs. So you can imagine each wall needs to have 1 ice pack sitting beside it. And at the bottom of the slide, you could see there are various different sizes and colors, mostly blue, but essentially just a cool box. So it's a box with a lid. And so these health workers, they'll carry these cool boxes, fill in ice packs, and go into reach out to people living in either in remote areas or in hard to reach areas. So I thought, coming from this cryogenics background, working always with systems that need to be kept at super, super cold temperatures, which is around minus 270 degrees C, I thought there must be a way to solve this. So that was the reason why it really inspired me to create my startup called Ideabatic. And it's called Ideabatic because there is a thermodynamics term called adiabatic, which kind of means that whatever you do to this system, there's a conserved energy within it, whatever you do to it. And so it kind of borrowed this term and changed it into Ideabatic, as in, okay, whatever happens to the startup or to the enterprise, we'll still be able to come up with ideas and solve these critical problems in the world. So that's why it's called Ideabatic. So let's have a look at the current vaccine carriers' performance. So they all share the similar curve right in the middle of the screen. So you can see once the 4 ice packs were inserted, there's a big temperature drop that goes below 0, and it goes back up again. And to stay in that between 2 and 8 degrees zone, then it warms up. So the first problem they all experience is that freezing temperatures. So that's the risk of some of the vaccines or medicine gets damaged. So there is a different kind of range of sensitivity of different vaccines, but for the safe zone, that is between 2 and 8 for all of them. And so you might wonder, oh, what about those COVID vaccines we have? Because some of them need to be stored at minus 80, or some at minus 20 degrees. So that is true when they're being stored at what I would call it a pre-last mile, which is like a first mile or middle mile, where they get transported via different nodes and then arrive at the factory. Sorry, not at the factory, at the hospital or at the clinics. And then before the injection, so before the vaccine actually go into human's body, these minus 80 degrees vaccines, they're actually powdered, so freeze-dried powder, so they need to be reconstructed into the vaccines that go into the human body. And so those vaccines, need to be stored at the fridge temperatures. So yeah, so this is what the current kind of vaccine cool boxes are like, and then this is how they perform. So you might wonder, so what do we use in the developed world? So say in the UK, instead of using ice packs, a lot of the areas use gel packs. So gel packs have certain chemicals in it. So they would get rid of that freezing issues at the very start. But the downside is with those gel packs, they don't last as long as ice packs. So they would stop like somewhere before, and then they warm up faster. So there's always this trade-offs here. So I want to show you, apart from the kind of the fundamental cooling problem with these cool boxes, one of the biggest issues we've found in the field is human error. So this picture is, I would say, my favorite photo because it summarizes all of the error that we're going to talk about. So this guy, so he's a health worker and he is trained, and he was told or trained to fill up the ice pack with 4 ice packs. So fill up the cool box with 4 ice packs. So as you can see, there are 4 slots here. So it's designed for 4 ice packs to go in. So in reality, he just put 1 in. And the reason why he did that, so I asked him, why did you put 1 ice pack rather than 4? And so he said, well, as long as there is ice, it's cold. So that was the kind of the mindset they have in there. So that's the first kind of human error, putting the wrong number of ice packs. The second issue here is that you can see this lid is opened. And this was really at the very start of the vaccinations. So he was still just writing some records, vaccination records. And he already opened this lid. And that lid was open permanently in the field during that 6 hour of vaccination. So you can see he's checking some things, and this box was already opened. So that's the second problem. So just leaving that lid permanently open, and it was 36 degrees outside. So you can imagine all the heat goes in and damage not just the vaccine, but also it cooled down. Sorry, it warms up the ice pack much quicker. And then, now the third one is that you can see all these vaccines are in a plastic bag, and then some of them are directly in contact with the ice packs. So that is also when the vaccines get damaged and they get frozen by that kind of direct contact. So what we did was we took 2 of the most commonly used cool boxes back to the lab, and then did exactly what they did, and then see what happened, what the temperature says inside the cool box. So we've got one smaller one, and then there's one a bigger one. So one of the experiments we did was, okay, let's see what happens if we had just 1 ice pack in this cool box. So as you can see, with 1 ice pack, the temperature only went down to about 17, 18 degrees. Then it warms up. So in this case, before they arrive, the vaccines were already hot. And if they put 2 or 3 ice packs, so the temperature would stay in that right range for about 5 hours. And so a lot of these journeys took us 5 to 12 hours one way just to walk to the village. So if that's the case, if you say the journey takes about 5 hours, and once they arrive, once they start using it, the vaccine's already outside that range. So really, they have to have that 4 ice packs there, as these cool boxes were designed to go down to that right range. But then, of course, that there's the first kind of freezing problems that they need to avoid. So one way of doing that is just to wait until it gets up to nearly 5 hours and put the vaccines in. But nobody ever done that in the field. So we did another experiment, which is that, okay, let's assume everybody put the right amount of ice packs in, so put 4. And then they remember to close that lid every time when they use the cool box. So what happens here, you can see, okay, it looks a little bit complicated, but let's just look at the red one first. So the red one is the humidity sensor. So that just tells you when we open and close it. So when the lid is open, then the humidity level goes down. And when it's closed, it goes up. So it just zigzag thing. It's just showing that we are doing that opening and closing action. And you can see that with a smaller box, within an hours of this vaccination opening and closing, it's already gone up above that safe range. And then with this bigger box, so it is better. It lasts for about 3.5 hours. So as you can see, these cool boxes, they are just not reliable when you start using them in the field. And so perhaps the person who gets vaccinated first, who get, well, cool vaccines, and who got vaccinated last, were just not so lucky. And so in this picture, you can see it's the same situation. So this nurse, she put only 2 ice packs into this cool box rather than 4. And so one of the things I found quite effective was that instead of telling them, oh, you've got to close the lid or you've got to put 4 ice packs, I'll just pull out this temperature sticker and then stick it onto the vaccines. And it says 20 degrees. And so all of them will, oh, okay, why? And they were all shocked. The vaccines were warm. And so then I started explaining, yes, so by putting just 1 ice pack and then putting the ice pack on the table and then put the vaccines out there permanently. And so that's when they started to realize, oh, okay, so why the training was done that way. It has to have 4 ice packs and these kind of things. So the question to ask here is, okay, what if there is a way for us to reduce that vaccine spoilage from 50% down to 5%, and to extend that cooling time from just a few hours when being used to a few days? But most importantly, even if we can achieve those things, the fundamental technical cooling time, can we avoid or prevent these kind of human error? Because that's what we saw the biggest issue there. Even if they're giving a perfectly functioning cool box, that leaving the lid open, not using the right ice packs, amount of ice packs, this all accelerate the spoilage, and then just it kind of equates to not having a functional device. So that is the reason why we started to develop a system that is first, okay, just making sure that the vaccines are kept at the right temperature. That's fundamental, most important thing. The second one is, can we build it so that it is fail-safe? And whatever they do, this device will still work. So this is what SMILE is designed for. So SMILE stands for Smart Last Mile Cooling System. So it comes with the main device that's doing all the cooling work, and then a backpack. But they come together as a system, and I'll explain to you why. The first feature I want to talk about is it has this self-closing door. So as you saw in that video earlier, that leaving that lid open was a big no-no. So we have a self-closing door. So it's very simple. So they can open it, take the vaccine out, and then they can go and vaccinate without having to worry about, oh, the lid or the door is not closed. So that's one way of minimizing that heat transfer. Now, the second one is that it comes with a single ice pack chamber. So it is only designed for that specific ice pack. It's a cylindrical shape. So that's one way of minimizing that human error of using, okay, 1, 2, 3, 4 ice packs. So we just have one. It's the same procedure, taking out of the freezers and then putting it in. And another advantage of having this concentrated core system is that when you have a bigger thermal mass in the middle of the system, it makes it harder to melt. So it has a smaller surface area. So when you open it, it's exposed to the surface areas that's exposed to the heat is just much less compared to you have 4 sides that are all exposed when you open it. And so you can see this chamber is completely separate from the vaccine chamber. So when you open that door, you don't get access to the ice pack. So they never get exposed under the sun. So once this ice pack is in, and the whole system would keep vaccine cold for 3 to 6 days. So that depends on the ambient temperature. So for example, at 20 degrees room temperature, it will last for 6 days. And because it's separate from the vaccine chambers, we designed it to be freeze-free, so there's no risk of freezing the vaccines, as in this traditional design where everything was squashed together and then some of them are in contact with the ice packs. Another feature here is an air locking mechanism. So that is one of the advantages where we can do a lot of this opening and closing without affecting the rest of the vaccines. So you can see when you open it, you're only exposed to that one chamber at a time, and then the rest is kept cool. So now the backpack. Oh, I forgot to talk about this number. So on the system, there are 18 chambers. So they're marked from 1 to 18. So on the backpack, there's a record sheet where the health workers can write down, for example, I have got some measles vaccines from chamber 1 to 5 and some yellow fever from 6 to 10, and some COVID vaccines from 11 to 15. And so once they arrive, all they need to do is to open this flap at the front and then turn the dial, say now, okay, I want to go to chamber number 10. So then you turn the dial to number 10, open the door, take the vaccine out, and the door closes itself. So this is another way to help health workers vaccinate more efficiently and also minimize that heat transfer. And so the backpack is designed to be just completely hands-free, as opposed to the current designs, crossbody or top handle, which can be difficult when they go onto these difficult journeys in kind of bumpy roads or need to cross river. Oh, this is frozen. Okay. There we go. Yeah. Oh, okay. So yeah, I forgot to talk about this bag. So it is all in one in a way that so you saw this pouch over there. That's like extra features for the health workers to put down their syringes, cotton, all the dry goods that they need. And at the moment, what they do is that, okay, one person carrying this box and another person carrying this vaccination record and another one carrying these syringes. And so it requires a lot of people to go onto the same trip. Whereas with this, they can have one person doing it or two. And with all of these pouches, so big or small, around the system. And one of the things so we did a trial in Madagascar, in remote villages there. One of the things they really like about the system is that they said they're now able to go to different villages in one trip. So, for example, they pack all those things from the local hospital or clinics and go to village A. Then they can continue going on to village B and C and to come back, rather than with the current box, they have to go out and then come back on the same day. And then we have another feature that we're developing at the moment, which is a add-on, like a modular add-on display that shows you the temperature and then the cold life. So currently, all these cool boxes, they don't have any of these features. And apart from the temperature being useful, what we would like to put as an extra isn't cold life, the remaining cold life. So what does that mean? So at this point, if you look at the temperature display, it tells you 5 degrees. Okay, so, but what does that mean? Does that mean in the next hour, we will still have 5 degrees, or it would be 10 degrees? So this cool life, remaining cool life, tells you, okay, we're at 5 degrees now, and then we still have 2 hours to work with, or we still have 2 days to work with. So that helps the health workers to decide, okay, maybe we don't have enough time to go to village A, but we have some time to go to village C. Right, so it is very simple. So the health worker turn the dial to the rider chamber, take out the vaccines, the door close itself. And so here, just showing you the data of the smile system when it's under this 30 degrees, and this just simulates the day-night cycle. When it's during the day 30 degrees and it's during the night 18 degrees. And then this is what the performance is. So it lasts for 5.6 days when it's not being used. And then we have another comparison performance here. So on this right, so at room temperature, so it lasts for about 6 days. That's when you don't open this door at all. Then we did also another opening and closing, so just simulating the vaccination procedure. So you can see that it is almost the same. So 5.8 days versus 6 days. So this is thanks to that, air locking mechanism and that self-closing door. So here, I'm just picking a few of the cool boxes that are currently used in the developing world rather than the developed world. So you can see that they are still quite similar. It's still a box shape kind of cool box. The difference here is that I think I mentioned earlier, some of them use gel packs rather than ice packs. So the downside is, yes, there's no freezing issues, but it doesn't last as long as the ice packs. And then some of them have more kind of advanced insulation packaging around it. And then some has a display that shows you, okay, what temperature it is right now. But you can see it's a cool box, so it will still have the same issues when you open and close it a lot. And at the moment, we are speaking to people who are doing research or doing clinical trials or are collecting biosamples who would also benefit from the Smile device. And if you happen to know there's anyone who would like to try this out and would really love to show you and to give you a few devices to try out. So this one, it's just a little clip of what it's like in the real life. So this was actually in a bigger model, and then that one is a smaller model. So the big model can carry about 700 doses, and then the smaller one about 500. And this is the evolution of the device from 2014, and it's got more simplified because it's designed for there's low resources settings, and so we want to have minimal kind of parts, and then it's also easy to clean, repair. So it's now this shape, and then it's got the minimal parts needed. So say if we can perform this function with 2 parts, then we will not use 3 parts. So this is to show you what the whole kind of procedure was like. So we spent a lot of money and effort at the first mile and middle mile developing these vaccines or critical drugs, and then they got sent onto these temperature controlled trucks and crates into the airplane. But then at the end, at the last mile, was just not very nicely controlled, and then also there were not enough good devices out there. So this is why it is such an important area that we really need to look into, and then to help solve that issues. So yes, thank you so much for joining me today. And if you have any questions or discussions, I'm happy to be involved.
Thank you, Kitty, very much for this presentation. I love this cool boxes, and I'm sure that a lot of people are going to be watching this this presentation in the future, because I'll make sure that people know that you have done something very innovative and creative. We are a very small group, so Salmia, Catherine, Peter, if any of you would like to ask questions, please open your microphones. We can have a conversation here.
Thank you, Milka.
Thank you, Kitty. Thank you for your time and wonderful presentation. Catherine, you opened your microphone.
I did, yes. Kitty, thanks so much. I have seen some of this before, but it was great seeing you put all of this presentation together. And I know you had a lot of interest in this technology. Do you want to talk a little bit about the sort of next steps, or what you're hoping to achieve in the next 6-12 months?
Yes, it's a great question. Thank you, Catherine. So for the next step, we actually have a trial coming up with the UPS Foundation and the Ministry of Health in Cameroon. So the aim is to interview 100 of these health workers on the on Smile and on the user aspect, whether they find it better or not as good as the vaccine carrier that they're using. So that's on the user aspects. And at the same time, we're also collecting the real life data. So we're putting these loggers in their current system, and just to monitor what the temperature performance is. And then also we're doing the same thing with Smile. So they would be going on to the same trip, so in parallel, and then we compare the two statistics together. So that's kind of like the immediate future, what the plan is for that. As for what happens after that, so that's actually something I don't really know yet, because in the last 7 years, say, we've been trying to talk to these big players who, in the first place, set up these challenges back 7 years ago, saying that, oh, these are the most urgent problems, the vaccine, cold chain, at the last mile. But unfortunately, these big players, they are, let's say, they are not so much of a pioneer as innovators. So they tend to kind of wait and see how other people see it, or how the other people use it. Then they kind of start slowly moving into that field. So that's when we realized, oh, these big players actually are not going to adopt these things in a very near future. So that is why we're kind of talking to those who actually really care about this problem, who want to improve their system, not just on the vaccine delivery. It could be on biosample collections or taking different drugs. These kind of applications. And then for them to kind of to work with them to take this device further, to go into manufacturing, and then to demonstrate more of these evidence, so that these big players can perhaps change the system, change the policy, to use these new devices to help people in these developing countries. So that is just unfortunate, but I realize that seems to be the way forward, or to be able to get this impact out quick, but not in a few years time, probably in 10 years time, for those developing world. But what we can do now is to make sure we find the right partner to take this forward, and then demonstrate that evidence for the big players. So yeah.
So Kitty, do you have a manufacturer interested, even if it's a small manufacturer? And what
Yes.
would the price be approximately?
Mm-hmm. So we actually, we have everything in place now, except the funding. So we have got a great manufacturer who we've been working together already without any kind of obligations, so no contract signed, but they're working with us to make sure that our design is manufacturable, because you know that a lot of engineering products, they can work as it is, but then when it goes to manufacturing, it's a different thing. So a lot of these designs need to be redesigned in order to be manufactured. But our design is ready, it's manufacturing ready. And then we've got a really good partner that we would go forward with when we have the funding. And so the challenge here is that a lot of this traditional investors, they don't like to put money into a device startup or company at this stage, because they find it too risky. They always said, where are your orders? And we will say, okay, we need to make the molds to be able to do a bigger trial, so that people will be able to order them. And then they just said, oh, well, it's too risky for us. When you have the mold ready, when you're generating revenue, and then that's when we're interested. And so we thought, oh, well, then if we're already generating revenue, we don't really need your money. so that is also like a forever dilemma for us, because we really need to get to that stage. And so the devices you see in that presentation, they're just built one-off for us, for the testing, for the trials, but it's really expensive to build one.
Yeah.
And so it has to go into manufacturing. So your question on what is the price point? So there is a range and estimate. So because this manufacturer, they can only do small quantities, so about 1,000 each time, a few thousands. So it's not estimated as, say, tens of thousands, that kind of scale. So just to give you an idea, if we make 1,000 units, it would cost about from 700 to 1,500 each unit. And just to give you an idea in comparison how much it is in the developed world, how much would this normal cool boxes cost? So let's just go back to here. Yeah, so these ones, oops. So like that one is about 200. So that's like on the cheap end. But this also lasts for less than a day, about a few hours. And so that one is like the most expensive one's about 1,800.
Oh.
So our price will be within that current developed world price range. And so if you were to compare that with the developing world cost, then of course our devices or any of these will be much more expensive than what they have. However, if you look at a different point of view, so we were looking at how vaccines were delivered. So here, if we take into account the spoilage that happened throughout this chain, so buying one of these versus buying the normal cool boxes actually help them save money. If you were to look at the whole big picture rather than just on the last mile. And also, of course, with the device, it can reach out to more people that it's currently just not possible. And that is human lives. And I don't know how I can put a price on it.
Right. But that's I'm very familiar with procurers in the public sector, and many times when we provide that as evidence, as one of the justifications for investing a little bit more, but gaining on health impacts, and that sort of doesn't ever enter into the equation, right? A lot of them go like, what's my bottom price? No, I'm currently buying the school box for $100. How do I justify in the public sector the procurement of a box that's $900 or $1,000? So it does become a big barrier for us advocates of better sanitary impacts. No, but it's interesting, and I really like that that design. When I got my COVID vaccines, I also wondered how reliable were the boxes where they kept the vaccines, and if they had just taken them out of the deep freezer or they had been sitting in that box for hours. But but congratulations, this is a wonderful device. Saumya, Peter, any comments?
Yeah, if I may. Thank you, Kitty, so much for this presentation. It was very clear, especially for a layperson. So thank you for explaining it in a very nice way. And congratulations on your innovations. It's fantastic. But, you know, sometimes when innovations are so innovative, it's hard for the world to catch up. And that's the problem, I think, that you're facing. It's too innovative for the world, even though it's obviously addressing a crucial problem. having said that, just to sort of validate and encourage you to continue being on this journey, I had a slightly different comment or a question, which is, could you talk a little bit about the design process?
Mhm.
Clearly, there's a lot that you are talking about from the engineering perspective of what are the requirements, what are the kinds of the efficiency of the product itself, how should the product perform, and so forth. In the global health field, there's a lot of discussion and movement towards human-centered design. So if you'd be able to comment a little bit about your design processes, that would be
Yes,
really
of course.
helpful. Thank you.
No worries. Yeah, I actually I have kind of like a lecture just to talk about that element. So looking at the design in various parts. So where do I start? So as you can see, it's got, you know, the self-closing door, that's kind of like one element, and then it's got also the vaccine holders, that is another element, and also there's the turning the dial in front. So all of this, and also the backpack, it also needs to be human-centered design. So let me maybe just pick one just to talk about. Let's talk about the simplest one out of all of this, is that self-closing door. So we have I don't know, maybe I can show you. I've got also just different evolution picture of different parts. Let me see if I can find one. There we go. Okay, let's share this one. Okay, so let's go down to, let's just go there. Can you see my screen?
Yeah.
So you could see this was the kind of first generation of the door, the self-closing door, and then there's also more, but then I just pick out kind of representable ones, and then to kind of the latest one. So you could see here we have got 1, 2, 3, 4 parts on the door. And so earlier I mentioned if we can have less part to perform a function, then we will not have more parts. That's on the user-centered side of things, that is to do with the repair and maintenance. So if you have more parts, you just increase more risk of things going wrong, or there's interfacing, there's you know, one needs to go into the different parts, and that's just trouble. And then there's the self-closing door. It has the main key thing is that spring. So the spring itself, we'll have to find out the right strength of it when it closes, because say if it closes too sharply, okay, it makes sure it closed, but it might cut off somebody's fingers if the fingers happen to be at the door. So that's another element of, okay, what is the optimal strength of that spring? So when we calculate it, we take into account, okay, how heavy is that door? What is the required strength? But in reality, okay, is that strength going to become a harmful thing? And then also another issue is that, okay, let's say we find an optimal strength for that spring, but if it's now on a bumpy road and then somehow by accident it roll off from this car down to the floor, and then when the thing dropped, and there would be this bouncing kind of element, and when it bounces, because of the spring, it would kind of experience that force as well, so it would pop open, the door would pop open. And so what is the element that we need to the strength that we need to look at to make sure that spring, okay, doesn't just accidentally pop open because it's bumped into something, or that it could snap somebody's finger. So all of that. And then of course we went to the field and then to test with the users. And so what we did was, instead of saying, okay, you got to use this way, or give them the instructions, we actually did a blind trial, which meant all the people were put into separate rooms, and then they have their own time to figure out how each part works. And so that's when we can confirm this is definitely a user-centered design, because they can figure out it themselves rather than, oh, we have a manual and you've got to do it this way. Because that's what we learned when we see people use the normal cool boxes. They are trained to put 4 ice packs in, but they never do that, or they need to close the door, or they never do that, just because they don't really understand why it's designed that way. So yeah, I think I kind of got off tangent now. So if we go to kind of further down that line, and you can see now we only have just 2 parts, so the bottom and then the top. And then it's just all of the little changes. So we also have like an area for the fingers, whether it is easier to lift up, at what angle. And that's all part of that human-centered design. And this is just the most simple part, which is the door. And there's also the other kind of vaccine holders, and yeah. Does that answer your question partly? Or we can talk about that more maybe in the next one.
Yeah, next time. But this is very illuminating. Thank you.
Great, thank you.
Thanks, Kitty. That was great. Really enjoyed it. I'm talking to you 5 kilometers from CERN, so you'll realize where I am. I'll come back to that in a minute. And it's nice to be talking to people, because I've just had my first negative COVID test today, despite having 3 vaccinations. Anyway, so one simple question, one straightforward question. What is the weight, and what's the maximum fully loaded weight? I'm just thinking of my back when I'm backpacking.
Yes.
And the second question is, are you intending, or have you maintained your contact since you're at CERN, or are you intending going back to Geneva? That's important because we've got Gavi here, COVAX, and all the development people at WHO, and one of my friends is a vaccine developer, and I'm really going to make sure she sees the recording when it's available. I'm not sure how many people know of this at this point, and I'm just wondering whether you have any intention of coming and making your product known here in Geneva with those organizations.
Great questions. The first one, yes, the fully loaded weight is 8 kilos. So there's been research on what is the maximum load that a human can carry. So that limit is 8 kilo, and that's also a number that's given by the WHO. Right, the second, okay, yeah, just to add that the backpack itself, it's designed to be like a mountain backpack rather than a normal one. So it's got this chest belt, it's got a waist belt. Actually, I'll show you. So we got one here. Right. So see, there's the chest belt over here. So it just helps distribute that weight. And then the, sorry, this is not the chest belt, this is the waist belt. And then there's the chest belt as well. That's your first question. The second question, whether I remain in contact with the CERN people, yes, definitely. Yeah, I absolutely enjoyed my time working there. So yeah, I still have been in contact with my colleagues. That's since 2013. So yeah, nearly 10 years, but we still, yeah. And also I go back to Geneva every year because remember that humanitarian hackathon I was talking about, where I kind of got into this humanitarian field. So they organize these kind of hackathons every year, doing the same thing, kind of look for problems and then match up with people and then helping with these projects. So I started with being a participant solving problems, into becoming more like a just mentoring, coaching the teams on the engineering side and also business. And then now I'm more involved as a organizer, so look for these challenges working with these NGOs, and then brought people, talented people together to tackle these issues. So yeah, that's why I'm in CERN every year for this. And then you mentioned Gavi and WHO. So those two are one of the organization or the big players I was mentioning earlier on the specific challenges. So I actually already spoke to the key people at the WHO who was responsible for qualification, these kind of things. And one of the challenges is, I think Milka mentioned, is everything is price sensitive, so price based. So what I was told was that, well, despite this is going to help or save money, save wastage in the whole chain, but what they're looking at is that last mile is, okay, this cost A, this cost B, and we're going to get the cheapest. And there are also a lot of challenges on, I think Samya commented on the innovation being a little bit kind of further from the reality right now. So that was also one of the points I was given. So when I spoke to one of the people in the WHO, they look at the design and they said, can you design your ice pack into a 4 ice pack design? So, like the normal cool boxes, they have 4 ice packs. And so I said, yes, of course I can, but we're not solving a problem here. Because the key thing is that when you have a 4 ice pack design, people would put 1 or 2 or 3. I've never seen anyone put 3 actually in these field trips. So at the end of the day, okay, I can design a system, the SMILE system, but have 4 ice packs, but at the end, it just does not function. So that was why I didn't want to change into this 4 ice pack design, but if it's say somebody who designed it for business to make profit, to make money, then they would, okay, yeah, they just change into 4 ice pack design because this is what WHO tell them to do. And for me, I'm here to solve a problem. So yeah, I don't see it as helpful when people are still going to use the old way. So why have a new device that is still going to fail? So that again is another challenge there, when exactly there's such a big jump from a normal cool box to a device that has all of these elements. And yeah, indeed, some people were suggesting doing this tiny incremental changes, and then to a point then they can accept all of your current design. And so yeah, so I think that was a very, very long explanation answer to your question on the WHO and Gavi. And so Gavi, they are much more open to innovation, that's my impression. And they were, in fact, interested in having a kind of a partnership. But after understanding what that involves, that kind of still meant having to go through the WHO system. It's the same thing. The COVAX is still the same kind of umbrella. So unless there is a system or a policy change so that they can adopt a new innovation like this to change or to actually use them. Yeah, I just don't see that as a way forward yet. I mean, so far. Yeah. You're on mute. Were you trying to say something, Peter? No.
Kitty was just smiling. So we're at the top of the hour, Kitty, and thank you so much. This has been a wonderful presentation and really a wonderful conversation with all our attendees. I'm recording the webinar in the web, so I will be sending the recording to all of you. And again, in the name of the Maternal Health Supplies Caucus and the Coalition, we want to thank you, Kitty, for giving us 1 hour of your precious time. And as Salmia said, keep on thinking new ways of really reaching that last mile that has been so challenging, not just for vaccines, but for other products like oxytocin, that is one of the products that we care for very much at the caucus.
Yeah.
So,
and I'm sure that's, sorry, can I just interrupt? I'm sure that's why Mariana suggested, because of course he's doing a lot of work on the quality of oxytocin, and the cold chain issue is a big one for oxytocin. Pity more people weren't on the call. But if we can amplify this by, you know, folks watching the video. But just lastly, I put it in the chat, you know, Kitty's invention, I think, is where she is now is a product of the fact that in global health, we don't seem to have worked a system out in order to move an innovation through the system in an easier way than she's finding. And it's just such a missed opportunity. We're very good at these sort of grand design things, making a big splash, wanting everybody to come with their designs. And then when they do, it's hard for them to actually move them along the value chain, which is such a pity. So.
Thank you, Catherine. And I did invite the working group that works on system strengthening, but I will send it out to system strengthening, to the new one, underused reproductive health technologies working groups. So I hope to amplify this recording a lot. So thank you. Have a great rest of your day.
Bravo.
Thank you so much, everybody, for joining.
Thank you again, Kitty, for the effort, and congratulations on this innovation. We'll make sure that we will broadcast and disseminate this knowledge among our members. So have a great day, and thank you for joining us again.
Bye.
Thank you.
Thank you so much. Have a lovely rest of the day.